In this Easy Ed video lecture, we're going to learn what are conductors, insulators, semiconductors, the difference between intrinsic and extrinsic semiconductors, as well as p-type and n-type semiconductors. Now let's first understand the materials. When we talk about materials in electronics, we compare them to their current carrying capacity, and they can be classified into three types, namely conductors, semiconductors, and insulators. Conductors are materials that have excellent current carrying capacity or allow good flow of current through them, such as a copper wire. And semiconductors, as the name suggests, allows partial or semiconduction of the current, or we could say its current carrying capacity is in between the conductor and the insulator, such as germanium. Whereas insulators are materials that are bad conductors of current and do not allow the flow of current through them, as they do not have a current carrying capacity such as wood. Now let's further understand this with an example of a stadium entrance and people. Let's imagine the stadium entrance to be a conductor and the people as current. Now we can see a large group of people passing through the gates and enter the stadium easily in the same manner in which conductors allow electricity to pass through them easily. However, here we see the crowd of people moving past the entrance one by one slowly in a queue. Now why is that? That's because the current in a semiconductor passes through it partially but continuously. In the case of insulators that are bad conductors of electricity, we can see the stadium entrance, which we have assumed to be an insulator, is blocked, thus not allowing the crowd of people, which we have assumed to be as current, to pass through it. The term semiconducting was used for the first time by Alexander Walter in 1782. However, the first documented observation of a semiconductor effect is that of Michael Faraday in 1833, who noticed that the resistance of silver sulfide decreased with temperature, which was different than the temperature dependence observed in metals. Semiconductors are further divided into intrinsic and extrinsic semiconductors, depending on their structure, properties, etc. Intrinsic semiconductors. Do we know what intrinsic means? It means in its purest form. Therefore, these type of semiconductors are in their purest form by the nature of their existence. The common semiconductors used are silicon and germanium, and they have 4 valence electrons orbiting in its outermost shell. We can further understand the motion of these electrons by looking at the structure of its atom. However, the atom needs a total of 8 electrons in its outer shell to become stable.
Hey, it's time to concentrate now.
Now let's see how the semiconductor atom acquires the additional 4 electrons and becomes stable. Let's first look at this process with the help of one atom. This atom already has its 4 valence electrons and requires an additional 4 to become stable, which it shares with its neighboring atom so that every silicon atom has 8 electrons in its outermost shell. Here millions of silicon atoms are bonded together and they form a semiconductor structure which looks like this. All these atoms set up a bond with each other, which is called as a covalent bond. However, these bonds are so strong that the electron fails to break the bond at 0 Kelvin. But as the temperature increases, the electron absorbs the heat energy and it is able to break the bond. Once the bond is broken, the electron becomes free to carry the current. We get a deficiency of an electron in the structure. Hence, there is an empty space formed which can also refer to as a hole. Therefore, we consider holes to be positively charged. Electron here is negative and the empty space or hole is positive. Therefore, the immediate neighboring electron gets attracted towards this hole and fills its place, thus creating another empty space or hole. At its previous position, the process will continue in the entire structure in a random manner. So let's understand the second type of semiconductors, which are extrinsic semiconductors. How are they different from the intrinsic semiconductors? While intrinsic are the pure form of semiconductors, impurities need to be added to the intrinsic to improve their conductivity. And these semiconductors with impurities are called as extrinsic semiconductors. Extrinsic semiconductors are further subdivided into p-type or trivalent and n-type or pentavalent. As we can see, we have 3 electrons orbiting in the outermost shell of the atom. It is called as trivalent. And in the other atom, we have 5 electrons orbiting, hence it is called as pentavalent. The common examples of trivalent are boron, gallium, and indium, and that of pentavalent are phosphorus, arsenic, and antimony.
Seriously, pay attention. This is important.
The process of adding these impurities to the intrinsic semiconductors is called as doping, and the impurities that improve the conductivity of these semiconductors are called as dopants. In case of trivalent, 3 electrons of boron will form 3 bonds with silicon, and in the 4th bond of silicon, there will be one empty space or hole, and as seen previously, the immediate neighboring electron will be attracted towards the hole, thus creating another empty space in its previous location. Simultaneously, the electrons of the silicon atoms attain thermal energy and keep breaking the covalent bonds at room temperature, thus creating further free electrons, and this movement will go on in the same manner. Therefore, the number of holes generated in this structure dominate over the electrons. Hence, this structure is called as a p-type semiconductor. Now let's look at the second type of extrinsic semiconductor, the n-type or pentavalent semiconductor. In this, the atomic structure of the n-type or pentavalent semiconductor will have 5 electrons in the outermost shell. As silicon requires only 4 additional electrons to attain stability, in pentavalent atom we have 1 extra electron as the valence electron. So we get a net negative charge due to this extra electron. Hence its name is n-type semiconductor. Common examples of n-type or pentavalent impurities are phosphorus, arsenic, and antimony. When we add pentavalent impurities to an intrinsic semiconductor, we observe that the phosphorus atom forms 4 bonds with 4 silicon atoms, fulfilling the needs of silicon. But even after that, there remains 1 electron which does not form any bond and remains free. Hence, unlike the previous structures, here we get free electron readily available for conduction. This electron rotates randomly around the phosphorus atom, following a circular motion. In addition to this, the breaking of bonds, as seen in the intrinsic semiconductors, happens here as well. Now let's have a quick review of what we have learned in this lecture. We categorize the materials into 3 main parts, such as conductors, having excellent current carrying capacity, insulators, having approximately 0 current carrying capacity, and semiconductors, having current carrying capacity between conductors and insulators. Semiconductors are further classified into 2 main types: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are the purest form of semiconductors, having 4 electrons in the outermost orbit and made up of covalent bonding of silicon atoms with each other. While intrinsic are the pure form of semiconductors, impurities need to be added to the intrinsic to improve their conductivity, and these semiconductors with impurities are called as extrinsic semiconductors. Extrinsic semiconductors are of 2 types: p-type, in which we add a trivalent impurity which has 3 electrons in its outermost orbit, and n-type, in which we add a pentavalent impurity having 5 electrons in its outermost orbit. Addition of trivalent impurity creates a hole in the structure, and addition of pentavalent impurity gives an extra electron required to carry the current.